Welcome to the pre-recording of lecture 13 of MCS 260. So this is in the summer course, so this is session 7, so the middle of the third week, first part, labeled as lecture 13 to correspond to what happens in a normal regular semester. So at this point in the course we have covered the a great chunk of the standard library of Python, so the data structures, tuples, lists, dictionaries, um, and we have also covered the main control structures, the sequence, the if, else, elif, and the for loops, also together with the while and the break statement. Now we still lack one, or we still lack many ingredients, but today we're going to cover one essential ingredient to write more, I would say, better structured programs. I was about to say more complicated programs, but that has a pejorative ring to it. Um, we're going to see how we can apply functions to structure the programs and actually start from what is called top-down design. So there are two parts in the slide presentation. I will explain a simulation algorithm. So we introduced simulation in the previous session. Today I'm going to focus on one particular uh, application of simulation. The computation of wait times when jobs are processed. And then in the second part, I will indicate the main concepts when working with functions. This is specific for Python. We are using Python syntax, but it's actually quite general also to all other languages. So the terminology, we had the body of the loop. We now actually have the body also of a function, or the definition of a function. We have arguments. We have when it is a proper function, we have a return statement, and we have formal parameters, actual parameters. And we will describe the mechanism, what happens with the scope of the variables when we look at local and global variables, what happens with the scope when functions are executed. So let's now look at the simulation. So suppose that we are responsible for the IT management and there is a printer that is shared by many users, and we would like to simulate the wait times for printer jobs. So the central question is actually that you have to provide some kind of rationale to buy or to not to buy a printer. Also, it can be used to estimate the amount of paper you would need each day given a certain distribution of the jobs. So in the simulation, we will simulate the arrival of jobs within a certain time interval, assuming that the arrival times are uniformly distributed and that the jobs are normally distributed. So every job has an average number of time to process. You can also see this as an average number of pages if you think about paper consumption, and there is a standard deviation of this. So the question is then framed more in mathematical terms. Given a number of jobs in a certain time interval, the jobs are taken from a distribution, a normal distribution, with a given mean and a standard deviation. What is then the average wait time? So this allows, if time is an issue here, should you actually buy now another printer? would allow the question. Now we've talked about data structures, so lists can be viewed as stacks and as queues. Here actually we will consider queuing. So there is an entire queuing theory subject. We will not get into this, but we are simulating aspects of queuing. All right, if we look at this as one program, then we can think about how this program will work. In general, when you have to do something complicated, things are starting to get really looking complicated if you try to think about everything all at once. But it starts to get a lot easier if you start to subdivide things in separate tasks. So every program has an input and the output. So what we do is we have the asking, the prompting for the first task. That's our first task. We ask the user for the number of jobs, the length of the time interval, and the distribution, the mean of every job, and the standard deviation. So at the very end, we print all the results. So at this part, actually, you think about the communication aspects of this. So here, this is just terminal oriented, but when we go later on into web interfaces, you could think about what kind of layout you would use for the forms that would be used to prompt to let the user fill in, and then how should it be displayed. Um, then we have the computations, the simulations, and the average time and standard deviation. So I put this in a separate function. So there is the central part. How will you run the simulation given the arrival times and the processing times of the jobs? So we will have two lists of the same length. One list contains the arrival and the other one contains the processing times. Alternatively, you could have a list of tuples where each time you have in each tuple the arrival and the processing time. But the center part is the simulation. So the generation of the jobs will could be done by two simple list comprehensions. The computation of the average and wait time and standard deviation, that's also a very straightforward computation. And you might even find built in some package functions that do this because this is a very standard, uh, frequently occurring task. The heart of this is actually the third function, that is the simulating. So we will spend some time on that. So one can look at a functional design of a program. Um, Here it is in tree hierarchy. So if you make pictures, so if you think about a top-down design, you think about a main, and often there is a function main in the program. Then there are the several functions, and here they are also labeled 1, 2, 3, 4, 5. This is also the order in which they are executed. So it doesn't need to be that way, and there is only the structure of this program is very simple. So there are only two levels in the tree. But it's a picture, and again, it illustrates kind of the simulate that is sitting in there. Uh, the central motivation, as far as I'm concerned, in introducing functions, is actually that you can separate the complexity of a program. So you can separate it into different functions. Um, Another motivation is that you can even if the code is rather small, you can group the instructions that are occurring frequently throughout your program. You can group this into what I would call here a utility function or a helper function that would format the numbers. All right. You can think functionally, but you can also think about the data. So you can see an algorithm as a sequence of data transformations. This is also a very useful way to separate uh, what is actually happening in the flow of the program. In Python, we first discussed the data structures. We did dictionaries before the if-else. At this stage in the program, you can also think about what would now be the uh, best data structures. I was organizing everything with lists here, but you can also work with lists of tuples. In step one, you are essentially returning a tuple. So we have a function that prompts and that returns a tuple. So one could think about a function that is y equals f of x, where x is a number, y is a number. But instead of having x, we can have no input, but we can return a whole tuple of inputs. So the parameters are n and t. So we have on input um, the t for the time interval, and the output are two lists, A, and I call the t again. This is very bad. It should have been P. I will fix this. So we have two lists, the lists of the arrival and the processing times. It's syntactically not entirely wrong, so the scope rules of the variables can change. As soon as you have the list of arrival times, you no longer need the capital T for the total length of the time interval. But nevertheless, it's not such a good um, practice. So the main step is now the simulation. Given two lists with arrival and processing time, compute another list, the list of waiting times, where all the lists are actually of the same length. Okay, and then we compute the waiting times, the average waiting times, and the standard deviation of every waiting time. Okay, this could lead to another distribution. So we have the normal distribution. Arrival times, if you're a statistician, you may have thought that Poisson distributions are indeed better. And indeed, Poisson distributions are better. But for the purpose of this lecture, uniform is just fine. Okay, so here is now the algorithm, and that is actually the heart of the simulation. The flowchart allows to zoom in on the on what actually really now is the essence of this entire simulation algorithm. So I have here used the right names. So capital P stands for the processing time. So there is a loop. So you see a loop that has an if statement in there. So there are two diamonds. So the biggest diamond is the stop condition. So we continue as long as the current counter for the current job is still less than the total length. So the letter I is actually an index. So in the initialization, we have already processed the first job. So what does it mean? So the waiting time for the first job, no matter when what the arrival time is, the first job within our time span never has to wait. So we initialize the list with 0. not with the number 0, but with a list that contains 0. Then the important variable is the B, the busy state. And it means that the processor or the printer, so I'm talking here about printer and processor, so this has general validity. So if you are simulating what happens in a checkout lane in a store, this would work just as well. So the important variable is is the little b, the busy state, and the printer will be busy as long for the length of the first job. So then we look at the time. So we are going to process now the job with index 1. So that's why the I is initialized to 1. So, and we compare the arrival time. So we have the arrival time of the job with index 1 minus the arrival time of the previous job. So the arrival times are sorted in increasing order. So that will be a positive number. Now, if that positive number is larger than the processing time of that first job, then actually you know that the printer is idle. So that means that the job with index 1 arrived past the arrival plus processing time of the initial job. And then you can reset the busy state to 0, and the job with index 1 has no uh, waiting time. Otherwise, the waiting time, we calculate this as the total time that has been spent, that has to be spent on the first job, minus the time that has elapsed. So between the arrival of the very first job and the job with index 1. So that's the false here. So there is never any waiting time when there is enough spacing, and you can see that if you look at the list of the arrivals, what we will do when we go to the Jupyter notebook. But you see then the busy state then gets updated again. So it could be that there is a waiting time, and actually the busy state then increases with the processing time with the job of index 1. And then we consider the next job. So I hope the logic is clear. So the loop looks complicated, but when you understand what happens in the beginning, if the logic sounds good, then you can continue reasoning about this. So you can see that we will return a list W, capital W, that is just as long as the list of jobs. So for every job, we will actually have the waiting time. And we will record in W the accumulated waiting times. Okay, functions in Python, how are we going to realize this? A function is defined in general. So a function has three parts. It has a name. You can call everything f, but as a function, but that will give you in trouble. The same with the arguments. So it's a little bit like figuring out what are good names of functions, what are good names of arguments. And then there is a body. Uh, these are the essentials. So the colon is also important. So you can give default values. So if we have the normal probability density function in PDF, then if suppose that we want to evaluate this, so then there is an argument and there are two parameters, so the mean and the standard deviation. Now, by default, the standard Gaussian distribution has mean 0 and standard deviation 1. So you can provide that as the default values. That makes it easier for the user. Um, a documentation string is also critical. So it's not strictly necessary. So if you have a function that is only one line, or if it's really clear what the function does, then it may not be necessary, but it is very useful. Already here, what is NPDF? Does it has to do something with PDF files? No, NPDF is the abbreviation of normal probability density function. So here I give a very short one-liner. We will see that you can make very long, with triple quotes, you can have documentation strings that span long sentences. Speaking of which, there are tools available that will generate Python code given a well documented, a well precise and a complete documentation string. So often people write documentation after they have a working program just to make sure to satisfy the pedantic requirements of the professor. But it's very good that you first think about what you really want that the function does before you start writing any code. And in the age of chat GPT, it might actually be also be a benefit. So if you don't really know what your documentation string should be, then you probably also don't really know what the code should be. In the age of code generators, garbage in, garbage out. So if you have a documentation string that's not really complete, like here, it's not really complete. What is normal probability density function? So what does it do? It does actually not describe this. It also does not describe the arguments. But it's good for what I want to show. So what we are doing is that so the argument, so the motivation for a function is that functions that are commonly used, you can put them into a separate file, and that separate file can contain many functions. A file can contain a complete program, but it can also contain a library of very useful functions. We've seen actually the mat library for that, or the mat module. So here is a way how we can define our module. And then it's actually very good to have documentation strings because they help if you do help. So here I have only one function and I named the module, the file, the same name as the function. This is fine if you have only one function. So you see same name for function and module. You see the documentation string and the header of the function. You don't see what the function does. Here it is. So we have essentially translating a formula from into an algorithm, a formula translated into a function. So it's a little bit a more complicated function, but it can be defined essentially in one line, but it's not going to be look very nice on the slide. So I broke it up into several lines. So we have a variable name result. So result is something that I made up. So you have the return result. So the value that is returned is the value that is computed in the result. There are the default arguments, so you can call the function. So I'm importing the module npdf, and then I have to call the function npdf of the module npdf as npdf.npdf. It seems a little bit bad, so you can actually import npdf from npdf import. I'm sorry, from npdf import npdf as f, for example. This could be better. You can call it with the default arguments, but you can also call it with keyword arguments. Mistakes that often happen is that here there are only three arguments, and the logic could be fine. First the arguments, then the mean, then the standard deviation. But it could also have been that somebody defined it as first mean, standard deviation, and then the name of the variable. If that is the case, then it could be confusing. So with the keyword arguments, you can actually switch the order. So this is very useful. We will later see that as a programmer, you can force the user of your function to use keyword arguments. And there's also a good reason here why mean and sigma are at the end, because we have default values for them. Okay, keyword arguments and names of parameters. Now, it is important to distinguish between what the formal parameters are, the names that we give to the arguments of the functions, and what the actual parameters are. Um, so here is a very, very simple example, but very critical to understand what actually happens when you execute a function. So the function will raise a value to the power 2. The value that we want to raise is 2. So we have 2 there is not a main program, so the Python interpreter will parse the definition of the function and will then execute the two statements which are seen as the main program. So the main program will take the value of the variable a, feed that into the function f, and what will be returned and assigned to b will be the square of the um, value that was passed to the function. So that is what the function does. A little bit in more stricter terminology, also the terminology you would see if you look into other languages which have different syntax for functions, but all other languages will also have a formal parameter. You could see this as a local variable, as a variable that exists only when the function is called. I will make that more precise in the next slides. And then there are the scope rules. So when you define the function, you actually do not know what is A and B. So you can't really get access to A and you can't really get access to B. So they actually cannot be used. On the other way around, so once the function has ended, x no longer exists. So you can no longer refer to x. So x actually has limited lifespan. So that's also the scope. So the scope of every variable determines when it is alive, essentially. Okay, so with pictures, so before the call, so after the execution of the statement a equals 2, we have that the name a refers to the object, which is an integer, 2. So then we get to the second statement, and it's another assignment, but when you do an assignment, the right-hand side of the assignment is first evaluated. And that is the function call. So during the function call, the value 2 is passed, and x is another name for the object 2. So at the call, x equals, or x is not equaling to, I should not use that term, but inside the function, we can replace now, wherever we see x, we can replace it by 2. But in more proper terms, the name x refers to the object 2. Then After the call, we are going to assign the value 4, so the function will return 4. So the 4 will exist. The name x will actually no longer exist. So that's why here actually, and I can probably emphasize this a little bit better than I do on my slides. So what happens is that after the call, x no longer exists. So I can wipe it out. The 2 still exists, so I can still refer to the 2 via the name A. I have a new object 4 that now can be accessed via the name B. Okay, I spent half an hour on this, so the topics in the lecture are important. We can write now many very interesting exercises. Deciding whether a word is a palindrome, so whether you can read a word forwards and backwards and you get the same word. That can be done via a loop. You can also solve the problem via a list comprehension. But then again, you're doing too much work. So you actually are looking over all the characters. When you are deciding whether a word is a palindrome, you will actually look at the list of characters, and we've seen how to peel off the list of characters. You will go with an index from the first character and compare it to the last character. And then increment the index, go from index 0 to 1 from the beginning and subtract 1 from the last index until first index and last index are the same. You will also break out as soon as you have the first character that is different. So when you think about the flow chart, if you are experienced programmer, you can immediately go to exercise 2. But drawing the flow chart is a very good exercise to think about the algorithm, how you would decide, and you can take any word in the sentence. Most of the words, the first and the last letter is already different. So you can decide very quickly whether a word is a palindrome or not. So write a good function for this. So I will go a little bit deeper into the code for the simulation. So add print statements that actually explain the states of the variables. Uh, Another extension is to work with multiple printers, multiple processors. So adjust the program to work with multiple processors. So then you have either multiple lanes, which probably is running the program, the simulate on different. That's not really good. But you have probably better one lane, but you have multiple customers. So you all have been part of a queue in a checkout lane. So you have one single queue, but then the person in front of the queue actually goes to the first available checkout uh, um, processor. Exercises 5 and 6 are more mathematical in nature. If we look at polynomials, we store the coefficients in a coefficient vector. Now it's very good that Python starts at 0 because the constant coefficient is stored at index 0 very naturally. So the power corresponds to the index. So when you evaluate a polynomial, you can evaluate from the highest degree and apply the power function. It's probably more natural to go from the lowest degree up till the end of the list of coefficients. You can work more efficiently, and so there is this infamous dot dot dot. So you can ignore the dot dot dot, and then in this case the d is 2. If you understand how to do it for d equals 2, and that's still, you don't need a loop for that, but if you write a loop for this and it works for d equals 2, most likely it will also work for any d. That's also the same comment I would like to make with the last exercise, which is a more complicated algorithm, but again more efficient. So you can evaluate a polynomial of degree d, or of any degree, with as many multiplications as the degree, as many additions or subtractions as the degree. It's very nice. Okay, I will flip to the Jupyter notebook. As always, you could look at the lectures from here, the last slide, which occurs now in the second half of the 50 minutes, well in the second half of this 50 minutes. But this is kind of the main goal of the lectures, that you can have an idea on how to start on the exercises. Okay, so let me pass to the Jupyter notebook that I have prepared. So there are two main motivations for functions. You have something that is widely commonly used, like all the commonly used mathematical functions that Python has grouped for us in the module math. So let's make our own module NPDF. It has only one function. I'm importing it here in a Jupyter notebook, and everything went well. I will say something why this was the case, and then I can type help. So here you see the benefit of a documentation string. My documentation string is now 3 lines long, and it explains the mean and the standard deviation. So with default values, it's still a title, so it's not really a documentation string that is going to tell what the function really does. So it should be more expansive of this. It returns the value of the normal probability density function evaluated at the argument, where the standard deviation is sigma and the mean is given by mean. So that's a more extensive um, documentation string. So you can try ChatGPT. So if you write a very elaborate documentation string and then ask ChatGPT, write a Python program for this, write a Python function for this, whether it will be possible. But there is kind of the definition that you will need to know, and perhaps you will spend much more time figuring out what is a good documentation string rather than writing down the 2 lines of code that we need for this. Okay, why did it work? It worked because there is a file. So if I would move the entire, so you see there is an npdf.py here, so in the file browser. So that's why it worked. But how did Python know this? Well, if you look at the path, there is the sys module that you have to that you can import, and from I only wanted to look at the path. If I import from this module the path, so path is so we will see more about modules, but modules can export functions, but they can also export data structures. So there is this list path that contains by default the current working directory. So that is first in the list. And you see all kinds of places where it's going to look for the module. So I have a mini conda installation, so it's going to look there first in the Python 3.10 folder. It's also going to look into some side packages. In the side packages, this is where you may find the additional packages that you have installed. Okay, we will see more. But the path is a list, and we can insert to that list. So we can, if we have stored our useful modules in a separate folder, with all our useful collections of softwares and data, we can import path and insert the location of this folder to the path. And then the import of our useful modules will work. All right, the second motivation for functions is that we can experiment. We can also an experiment, I mean, that we can build, give a better structure to our programs. Often a good rule is also is that if you need only one line of code for a function, it might not be uh, a good enough motivation to define a function, except if you want to emphasize that line, except also if you want to use that line separately. So it's a way to what we call parameterize your software. If your program changes, you only have to change one function definition, not everywhere where you have done it. So you avoid duplication of important pieces of code. Um, so here for the simulation, the heart of the simulation was actually the simulate function. And the generation, so this is also a way how I'm very much in favor still for using the Jupyter Lab notebook when you design programs. The make jobs will return two lists: arrival times and processing times. Now, I glanced over this, but the arrival times, they need to be sorted. So sort is a very important and very useful method on lists. So here you see an example of the input. For the critical parameters, number of jobs is 10, and the length of the simulation interval is, say, 60 time units. Here I'm thinking about 60 minutes now, 1 hour. But you could also think about 24 or 8, which is the 8 days in a working day. You see the arrival times, and then we have the processing time. So the normal distribution in the random module is available in the function Gauss. Here I felt 5 was good, 3 for the standard deviation. Note that this program is not entirely that robust. It's possible to generate that way negative processing times, which is of course unrealistic. So you would have a job that gains, that gives you time rather than taking time. But in computer science, a lot of things are possible. Reverting time is not good when you think about applications. So in order to make it a little bit more robust, you would actually put an absolute value at least before the processing times, because you don't want negative waiting times, which would say that your job would finish before you submitted it. Okay, so the key was the simulation function. So what I did, I wrote actually the Python script first. I designed this before I was working with Jupyter notebooks, when I was a programmer just working plain with Python scripts. But the Jupyter notebook allows me to pull out the central, the essence of the simulation and actually run it already. So I have two lists, A and P, and what returns is the list of waiting times. So here in this case, it contains the value of the busy variable, but often modified. So it's actually not really the state. So it contains the values, but sometimes it's modified with the difference of arrival times. Um, So an exercise to study the simulation is really print out the state table. So we have the I, the number of rows, and then we have the value for the busy variable. So what you print out is I, and you print out the busy variable. Eventually, you also print out the arrival time and the processing time. So this is here defined in a computer science language, but you could also build a whole story around this. Instead of seeing the state table as rows and columns, you could see this as you could make a story. Job so and so arrives and takes so much time to process. There is so much, this is now the new value of the busy counter. And then you can read the story and verify the correctness and understand it much better. Okay, I have 2 minutes or I have 5 minutes left, less than 5 minutes, to look at the complete program. So if you read the complete program, you see the functions one after the other, and it's kind of boring. So the formatting of the data, well, this is what happens multiple times. It's very useful to format the data not with complete floating point numbers, but with numbers that have only two decimals after the dot. So every list you will print, so this will essentially be your string representation of every list that you show. So that's the form. Um, then the prompting, and in some sense this is no longer that trivial. This program will not be so user friendly, because suppose that after entering three numbers the user hits a character, and then the cast to a float will fail. So to make this function now much more useful and much more robust, you could have some type checking there. So, and we will get into that later. So we can test on the type, but you can also build in exception handlers. So that will uh, ask the user to retry in case the input is not an integer, is not a float. And you can also check for other values. So for example, the mean should not be 0. So that's a very bad value for a mean, because then you have also negative values for the job processing times. Okay, in the making of the jobs, that's actually the setup. So here I did this, so in the Jupyter notebook, I did it with the list comprehension. Here I'm doing this with the insert. So I'm inserting each time at the front. So I'm actually using the stacks, not really the append. But I'm going to sort everything anyway, and I'm sorting the arrival times. You could say, well, wait a second, these are actually should also sort the corresponding processing times, but everything is random anyway, so it doesn't really matter. So each time we print the current arrival time, current processing time. This is as it is generated before the sort. And then we have the simulate. I went through this already. And then we have the average and the standard deviation. In some sense, I'm running over time here almost, but this is the main program now. The main program is where in this top-down design I could have started. So we had the first picture with the tree. You see the data flows. So the ask function that returns a tuple, the make jobs that returns the tuple of lists, and given the input parameters. We print the arrivals, the job times, the formatted lists. Then we compute the wait times. And finally, the end of the output, the outcome is the average waiting time and the deviation. I should run this. So here actually you see the result of a run, and you see that I had, even with the standard parameters, I had a negative job time, which is actually very absurd. So let me run this again. So just to indicate that this is unlikely to happen, but it may happen anyway. Let me choose 5 and 3 again. And then you see, oh, I am again unlucky. I have again a negative processing time. So you can see that this is actually not really a realistic input. So perhaps I could say 7 is the length of the time, and there's only 2. Well, I'm sorry. Um, so now I have so 1 as a standard deviation. Um, so I have 10 jobs now between 0 and 7, so 7 time units. The mean is 2 and the standard deviation is 1. So you see, in that case, there is a large waiting time and also with a large deviation. It definitely matters if you submit your jobs at the beginning or at the end. Okay, I will go back to the slides. I hope that you can now see that we can make more interesting exercises. The exercises will also take longer. Um, so the application that we have seen would take the place of an entire project. So I'm very well aware of this. So that's why the exercises are splitted in two. So 1 and 2 are actually joined together, 4 and 5 and 6 are actually also together. Okay, I hope this was interesting.